So my name is Zach Hilliard. I'm in the mathematics department, and I'm going to be talking to you guys today about my thesis research on quaternion valued solutions to the KdV equation. And in particular, we're going to be looking at non-uniqueness and the tail behavior of one soliton solutions. So to start off, we kind of have two main ideas of this research. The first one is solitons, and the second is quaternions. So solitons are a kind of wave. They were initially observed by an English engineer named John Scott Russell in 1834. He was sitting along the Union Canal in Scotland, and he was watching as a boat was pulled into the harbor. He noticed a strange phenomenon. There was a wave coming off the bow of the boat, but unlike traditional waves on the beach, it was translating at a constant speed, and it was maintaining its shape as it moved across the canal. So later on in the 1890s, the mathematicians came in, like we do. We kind of came up and cleaned up after him and formalized his observations and actually wrote it down into a partial differential equation. That equation is given here, and it's known as the KdV equation. It's named for the two mathematicians that discovered it. And this equation models that wave behavior. It emits soliton solutions, and it's also pretty neat because it's an integrable equation, meaning that a large class of its solutions can be found explicitly, which is not a very common property for partial differential equations to have. Now, solitons in general, there are more equations that can admit soliton solutions, but in general, there are three main properties that these solutions tend to have. So the first one is that they translate at a constant speed and the waveform is localized. So in this top animation, you can see a soliton. It's translating from right to left along the x-axis. And this is actually a KdV soliton. So you can see that it's translating at a constant speed and that the waveform remains constant. It doesn't really change that much. The third property is that after a collision between two waves, the waveform remains mostly unchanged. So in the second animation, what we can see is two solitons. This is what we call a two-soliton interaction. And we can see that as they collide, before and after the collision, their shape and their speed actually doesn't change. There's subtle differences with their positions of where they should be if you plotted them individually before and after the collision, but that's a little bit beyond the scope of this research. So the next thing that the next main idea of this research was looking at the quaternions. Now, the quaternions are a four-dimensional number system that were developed by an Irish mathematician named Sir William Rowan Hamilton. Interestingly, he also kind of came up with the idea while he was walking along a canal in Ireland. But his idea was to generalize the fact that we can use a complex number to represent a point in two-dimensional space to three-dimensional space. So he was trying to figure out a way to generalize, points in space as one number, but it's actually was proven after he was trying to do this, it was actually proven to be impossible. You can't actually represent one number or one number in a specific way with three components. So, but what he was able to do was generalize to four dimensions. And by doing so, he actually created two more imaginary units. So the numbers I, j, and k are actually defined to be the square root of -1. And we can build a four-dimensional system like we can see in this first equation. So the quaternions are given by this set H, and they're defined as the sum of individual real numbers. We call them q sub 0, 1, 2, and 3, multiplied by I, j, or k. So we have four parts to this number. We have the real part, which is q0, and then we have the I part, the j part, and the k part. Now, the problem with making this extension is that as you go from 2 to 4 dimensions, you actually lose commutativity of multiplication. So the order that you multiply numbers in actually matters now. So a times b is not the same as b times a anymore. And that is actually defined in this third equation. We have that ij equals minus ji, which is equal to k. And we have similar expressions for ik and jk. Now, addition is commutative in the quaternions, so that's no big deal. Works exactly the same as we would if we were adding kind of component-wise. So we're adding the real parts, the I parts, the j parts, and the k parts. So what we were able to do was we were kind of putting these two ideas together. So we were taking quaternion valued solutions to the KdV equation. So KdV can actually be extended to take non-commutative solutions U, and we make this extension in this third equation, or in this equation 3 here. We'll refer to this as QKdV, but we're really just kind of extending it to take non Noncommutative Solutions. So we're continuing the work that was set up last year by John Cobb, Alex Kasman, Albert Cerna, and Monique Sparkman. They were able to publish a paper last year on quaternion valued solutions to KDV. And kind of one of the biggest things that they found was that you can actually produce solutions to QKDV by considering quaternion constants alpha, beta, and lambda, and then building up this function phi. Now, if you take phi and then you take its x derivative and its multiplicative inverse, define their product, and then multiply 2 times that product's x derivative, you actually end up with a solution to QKDV. Now, they were able to find that there were 2 equations, or 2 main types of solutions that come from this method. The first one is a breather one-soliton. So we still have that constant speed translation, that localized waveform, but as it translates across the x-axis, it actually expands and contracts and looks like it's kind of breathing. It has that kind of throbbing nature. So that's where it gets its name from. The next kind of solution is a translating periodic solution. The name kind of gives it all away. It just looks like a group of periodic functions that are translating across the x-axis at a constant speed. For our purposes, we're going to focus mostly on the breather one solitons because they're a little bit more interesting, and that was kind of the question that we were trying to answer is, surrounds breather one solitons. So what's the problem with this method? The method that they found in the previous paper is actually really nice because we can produce solutions, but the problem is that 2 different phi functions can actually map to the same solution. So if you take 2 solutions or 2 phi functions with alpha, beta, and lambda given on the left, you'll end up with this breather one soliton. But if you take distinct or different alphas, alpha hat and beta hat, and create a new function called phi hat, it actually gives us the exact same breather one soliton. So a natural question that we need to answer is, okay, what are the conditions on alpha, beta, or alpha and beta that will actually map to the same solution? We have to have lambda the same because lambda controls the speed. So the lambdas always have to be the same, but the alphas and the betas can be different. So in order to answer this question, we were actually able to develop a set of 10 equations that must be satisfied in the event that 2 breather one soliton solutions to KDV are equal. So all of these solutions relate the parameters alpha, beta, alpha hat, beta hat, and lambda in different ways. And when 2 solutions, U and U hat, are equal, these equations have to be satisfied. So we're actually able to develop a really large class of equations that determine the equality of solutions. Now, the next thing that we looked at was the tail behavior of one soliton solutions. So we have this localized disturbance in the middle, which is our soliton, but outside of that local area, the solution is very small, but not exactly 0. So in order to examine this behavior, we decided to take our solution U and divide it by its length, or its modulus. And what that does is it kind of makes everything, when you graph everything, the highest kind of value that it can attain is 1 or -1. In doing so, we actually end up with these really interesting periodic functions, and that's shown in this bottom image. So we have these periodic functions on the right-hand side of the localized disturbance and the left-hand side. We can see this kind of little blob right in the middle along the y-axis. That's actually where the localized disturbance is. And these functions on the right and the left appear to be different. So 2 natural questions that arise are, what are the equations that govern these periodic functions? And also, are these 2 sides ever equal to each other? Do they ever match in some way? So we were actually able to answer both of these questions. The first one was a pretty lengthy expansion of our equations for U, but what you can derive is that the periodic functions on the right and the left for a normalized breather one soliton solution are given by these equations. On the top, we have the equations for the right-hand side of the disturbance, and on the left, on the bottom, we have the equations for the left-hand side periodic functions. Now, H is a constant, it's a real number, and it just has a very messy, expansion. You can derive it from Mathematica, and it's in the paper that I wrote, but I chose not to include it here because it doesn't look very nice. It's very, very messy. The next thing is that we were able to answer the question of when the left-hand side and right-hand side will ever be equal. And in the case that the left side periodic functions and the right side periodic functions are ever equal, these 2 equations have to be satisfied. So ultimately what we were able to do was we were able to develop a set of equations that determine when 2 breather one soliton solutions to QKDV are equal. We were able to find the functions that arise when you normalize a breather one soliton, and we were also able to determine when the left side periodic functions and the right side functions were equal. Right. So are there any questions?